Up till now, we discussed the lossless or low loss transmission lines. We studied the characteristics of lossless transmission lines and also saw various applications of lossless transmission lines. In practice, however, as the frequency increases, the loss increases and the line becomes lossy. Today, we will see briefly the characteristics of a lossy line. Of course, if the line is very lossy, then it is not very efficient medium for transferring power from one point to another. So, when we say a line is lossy in practice, it is not very lossy, but it is moderately lossy. So, first we will see very briefly, if the line was very lossy, how the characteristic impedance and the propagation constant of a transmission line will change, and then we will go to the moderately lossy transmission lines. So, if I consider a very lossy line, which we can define when the resistance is much greater than the inductive reactance and the conductance is much greater than the capacitive reactance, we can call that line as a very lossy line, compared to what we had defined for a low loss transmission line, where the reactances were much larger compared to the resistive component. So, for a very lossy line, we can say that if R is much greater than omega L and G is much greater than omega C, we can call this line a very lossy line. For this line, then the characteristic impedance Z0 will be square root of R plus j omega L divided by G plus j omega C, and now R is much greater than omega L, G is much greater than omega C. So, this is approximately square root of R by G, which is a real quantity. Similarly, the propagation constant gamma which is square root of R plus j omega L into G plus j omega C, that is approximately equal to square root of R into G, again is a real quantity. So, first thing to note here is that if the line is very lossy, then the characteristic impedance is real, but the propagation constant also is real. Of course, when the line was lossless, the characteristic impedance was real. So, the realness of characteristic impedance does not tell you whether line is lossy or line is lossless. In both the extreme cases, when the loss is very small or when the loss is very large, the characteristic impedance turns out to be real. So, looking at the characteristic impedance, we will not be able to judge whether line is a very lossy line or the line is a lossless line. However, if I look at the propagation constant, for a lossless line, the propagation constant gamma was purely imaginary. The alpha was equal to 0 and we had gamma equal to j beta. However, for a very lossy line, the gamma becomes a real quantity, that means it has only alpha and beta is equal to 0. What that means is, now there is no phase variation in space for whatever voltage or current variation we have on this line. And if there is no phase variation on the transmission line, then it does not represent a wave phenomena. So, essentially in this case, when the line is very lossy, this structure is not even representing a medium which is carrying voltage or current waves. So, we have a voltage and current variation on this structure, but this variation does not represent the wave phenomena. So, you have a voltage which varies now exponentially with the attenuation constant which is given by square root of Rg, and there is no phase variation. So, there is no travelling wave which is set up on the structure. So, obviously, we are not interested in this phenomena, we are investigating the wave phenomena on transmission lines. So, we are essentially considering the case where this condition is not really prevalent. What we have is R and G, they are comparable to these two quantities. So, R is comparable to omega L, G is comparable to omega C, and that line then we can call as the moderately lossy line. Even in that case, however, the standing wave characteristics on transmission line change, and we will see how the standing wave patterns will get modified if there was a significant loss on transmission line. So, what we are now considering is that yes, the waves are there on transmission line, and gamma is in general a complex quantity. So, alpha is not negligible compared to beta. So, we have in general the propagation constant gamma, which is alpha plus j beta. So, the travelling wave exponentially decays with a attenuation constant alpha, and it has a phase constant which is beta. Once I get this, I can go back to my original voltage equation which I derived for the general line, and then ask in this condition how the standing waves will get modified on the transmission line. So, if I write down now the voltage on the transmission line, which is again V plus e to the power gamma into L plus V minus e to the power minus gamma into L, and if I substitute for gamma as alpha plus j beta, this is V plus e to the power alpha L e to the power j beta L plus V minus e to the power minus alpha L e to the power minus j beta L. So, if I look at the first term here, it is telling me that as I move towards the generator, this wave, which is the forward travelling wave, the wave going towards the load away from the generator, exponentially grows towards the generator, or in other words, as I move away from the generator, this wave exponentially decays. Similarly, this wave exponentially decays towards the generator or exponentially grows towards the load. Depending upon the value of V minus and V plus, or the ratio of V minus and V plus, which is related to the reflection coefficient at the load, you may have a certain amplitude of the reflected wave compared to the incident wave at the load point. Then the two waves travelling in the opposite directions grow or decay exponentially as we move towards the generator. So, at every point, now if I look at the superposition of the waves, first of all, if there was certain ratio of V minus and V plus amplitude, in the lossless case this ratio was same at every point on line. However, that is not true now, because the amplitude of this wave is exponentially changing with e to the power minus alpha L, amplitude of this term is changing with e to the power plus alpha L. So, ratio of the amplitude of reflected and incident wave now become a function of location on the transmission line. So, let us say if I draw these travelling waves on the transmission line. So, this is my load, the L is measured towards the generator, there is having some impedance ZL, and from here I know the reflection coefficient, I can calculate at the load point. And if I now plot the incident wave exponentially decays as I move towards the load. So, if I plot the magnitude of the incident voltage wave, that wave will be exponentially dying down like that. So, this represents V plus e to the power alpha L. Depending upon the load value, I have a certain reflection coefficient at the load. So, the value of the reflected wave will, let us say, be something this at the load point. This now exponentially dies down as I go toward the generator. So, this is V minus e to the power minus alpha L, and then total voltage will be superposition of these two at every point. So, here the voltage will be this plus this, you can get something here, and I can add similarly, and the phase is changing. So, as I move now on the transmission line towards the generator, the standing wave amplitude does not remain constant, because this wave is becoming weaker and weaker, reflected wave. The incident wave is becoming stronger and stronger towards the generator. That means the reflection coefficient, which is the ratio of these two, is becoming smaller and smaller, and if that is becoming smaller and smaller, the wave is appearing more and more like a travelling wave rather than a standing wave. So, if I look at the standing wave pattern on this line, it will be something like this. It will start like that, and then the reflection is becoming weaker and weaker. So, slowly it will merge with this line. So, if I go close to the load, I see a standing wave, but as I move towards the generator, the standing wave becomes weaker and weaker, and it merges with this line, which essentially represents a forward travelling wave. So, that means even if we are having a very large mismatch at the load end, as you move towards the generator, the mismatch becomes weaker, or the matching improves, or you see the impedance from this side, which is very close to the characteristic impedance, because you are seeing only the forward travelling wave from the generator. So, one may then wonder that if I have a lossy line, irrespective of what is the load impedance, I will always see a match from the generator side. But this is not a very good situation, because although we are seeing match from this end, the power which is supplied by the generator is not delivered to the load. In fact, substantial amount of power has been lost in the transmission line. So, in this case, saying that I got a match at the input does not have much meaning, because now even if the load is matched at the input, the power is not delivered to the load, power is lost in the transmission line. But if we are interested only in getting a match towards the end of this line, that is towards the generator, and I am not too much worried about the efficiency of power transfer, I simply want that reflection should not come and hit back the generator. Maybe that is a very good technique. We can introduce deliberately a lossy transmission line between a mismatched load and a generator, and even if the full power is not transferred to the load, at least generator does not see any reflection. So, its characteristics do not get modified. So, many times in practical work, a deliberately lossy piece of transmission line is introduced, so that even if in experiment you connect some arbitrary loads to this, and even if you have very strong reflections, at least these reflections will not go and damage the generator. So, here the purpose certainly is not maximum power transfer. The purpose is to protect the generator from any unwanted reflections coming from the load. So, in that case, definitely a lossy line can be used for avoiding the reflections coming back and hitting the generator. Nevertheless, if you are having now a general transmission line, the standing wave are going to go like this. So, in general, then we can write down now the reflection coefficient. So, the reflection coefficient now at any location L, gamma of L, that will be V minus upon V plus e to the power minus 2 alpha L e to the power minus j 2 beta L. And as we have seen earlier, at L equal to 0, the reflection coefficient is the reflection coefficient at the load end. So, V minus upon V plus is the reflection coefficient at the load end. So, we know V minus upon V plus, that is equal to gamma L, that is equal to ZL minus Z0 divided by ZL plus Z0. So, the magnitude of reflection coefficient is gamma L e to the power minus 2 alpha L or mod gamma L e to the power minus 2 alpha L, and the phase of the reflection coefficient is minus 2 beta L. So, if I go now to the complex plane and ask, as I move towards the generator from the load point, what kind of curve will be traced on the complex gamma plane? Or if I know the reflection coefficient at the load end, which is this, as I move towards the generator, how the reflection coefficient will change? One thing is immediately clear. If I substitute for V minus upon V plus as gamma L, this reflection coefficient at any location L will be equal to gamma L. Let me write down this as magnitude of this, and the phase of this will write explicitly e to the power minus 2 alpha L e to the power j theta L minus 2 beta L, where theta L is the phase of the reflection coefficient at the load end, mod of gamma L is the magnitude of the reflection coefficient at the load end. So, the total phase at distance L is theta L minus 2 beta L, and the amplitude of the reflection coefficient at location L is mod gamma L e to the power minus 2 alpha L. So, as we move towards the generator, L is positive. So, the amplitude of the reflection coefficient goes on systematically reducing. So, this one, as we have seen earlier in the complex gamma plane, the variation of phase gives me a rotation in the gamma plane because the angle is reducing as I move towards generator. But that time lossless line, this quantity was constant because this was not there. So, it used to trace a curve which was a circle. However, now since we are having this term, the radius of this circle is reducing continuously. That means this curve now essentially draws a spiral on the reflection coefficient plane. So, if I take the Smith chart, which is the complex gamma plane, and let us say initially the point was something here, that was the reflection coefficient magnitude. As I move on the transmission line towards the generator, I do not get a circle, but I will get a curve which will look more like that. Because the radius of this is reducing continuously because of the loss of the transmission line. So, the point as we move towards the generator comes closer and closer to the center of the Smith chart. And as we have seen earlier, if the point is closer to the Smith chart, it represents an impedance closer to the characteristic impedance or better match conditions. That is what we have seen earlier. As we move towards the generator, you get the reduction in the reflection coefficient, and therefore the impedance appears more and more matched. So, one thing one can note here is that on a lossy transmission line, the point moves on a spiral as we move along the transmission line. The quantity which we have used for measuring the contribution of the reflected wave was the voltage standing wave ratio, which was the ratio of the maximum voltage to the minimum voltage on transmission line. You will see now that this quantity is not a very meaningful quantity because I cannot really uniquely define this quantity on the transmission line. If I look at now the standing wave pattern, which is this pattern on the transmission line, if I get this voltage maximum and this voltage minimum, I will get one ratio. If I take this voltage maximum and this voltage minimum, I will get another value. That means the VSWR is not uniquely defined on transmission line. In fact, the VSWR has lost the meaning because it is no more a characteristic of the load. It also has become a function of the transmission line characteristics. As a result, now the VSWR is a function of length along the transmission line. So, in case of a moderately lossy line, the VSWR is not a very meaningful parameter. If the line was low loss, I can still say, well, what value I get from this and what value I get from this. I can take maybe mean of these two quantities, and that is the VSWR which is in this region of the transmission line. If I go somewhere here, I will get another value of VSWR and so on. So, in general, when we are having a moderately lossy transmission line, the VSWR does not serve any purpose. So, we have to really go to the quantity which is the reflection coefficient quantity. Also, you will note that now since there is a loss and this function is no more a sinusoidal function, the separation between the two minima is not exactly equal to lambda by 2. So, if I get the minimum point here and if I get the next minimum here, this separation is different than half wavelength, which we get just from the phase relationship. However, this, as I mentioned, these are the extreme cases where the loss is very large. In practice, most of the transmission line have a loss which is reasonably small. So, we can still make an approximation that separation between the two minima is almost lambda by 2, and the VSWR is more or less same, at least zone wise on the transmission line. One can then ask, if I have a moderately lossy transmission line, how do I make use of the Smith chart? Can I make use of the Smith chart for impedance and other calculations? The answer is yes and no. Strictly speaking, if you want to do the impedance calculation by using Smith chart, you have to draw the spiral. Unless you draw the spiral, you will not get the correct variation of the reflection coefficient or the impedance variation on the transmission line. However, if the loss is small, we can make this spiral like a circle and apply a correction after every lambda by 2 to the radius of that circle. Essentially, what then we are saying is that ideally the amplitude would have reduced for the reflection coefficient, which will go something like that. This is the mod of gamma as a function of L. So, reflection coefficient value will reduce as I move towards the generator, and this variation essentially was giving me the spiral. What we say is, let us divide this transmission line in sections of lambda by 2. So, this is, let us say 0, then this is lambda by 2, this is lambda, this is 3 lambda by 2, and so on. And let us make an approximation to this curve, a staircase approximation for every lambda by 2. So, I say that for this distance, the reflection coefficient is almost this, then this lambda by 2 it changes to a value which is this, then 3 lambda by 2, though it like that, 2 lambda is like that, and so on. So, what we have done is, we have now done a staircase approximation to the actual curve of the magnitude of the reflection coefficient. So, we are approximating now, saying that between length 0 and lambda by 2, the reflection coefficient value is this. Then after lambda by 2, you apply a correction, you change the value to this, you change the value to this. So, every lambda by 2, you apply a correction to the magnitude of the reflection coefficient. Or in other words, what we are saying is, on the a Smith chart, let us say you take this point, first you draw a circle for 1 lambda by 2. If we move a distance more than lambda by 2, after 1 lambda by 2 movement, find out what is the change in the magnitude of the reflection coefficient, make a correction, and then move on the second circle here for next lambda by 2. If you have to move further on transmission line, again make a correction to this, draw a next circle here, and so on. So, every distance of lambda by 2 on transmission line, I make a correction to the magnitude of the reflection coefficient, and then assume that for the next distance of lambda by 2, the reflection coefficient remains constant, its magnitude remains constant. So, this correction, if I call this as a correction, let us say this quantity is some delta. This delta will be, so this quantity delta will be nothing but a reflection coefficient at a location into 1 minus e to the power minus 2 alpha into lambda by 2. So, at any location on transmission line, the reflection coefficient will be gamma. After a distance of lambda by 2, the reflection coefficient would change to gamma e to the power minus 2 alpha into lambda by 2. So, the difference in these two quantities is nothing but this correction. So, if we are doing calculations on transmission lines which has a length much larger than wavelengths, then every lambda by 2 you keep applying correction to the magnitude of the reflection coefficient, and then essentially solve the problem. As I said earlier, if you want to have a very accurate analysis, then ideally you have to really draw the spiral on the Smith chart. Of course, nowadays with the help of the computer, you can even draw the spiral on the Smith chart and can do the accurate calculation. However, if you are not using a computing tool, then maybe the approximate steps which I mentioned here will be very useful in analyzing the impedance transformation characteristics on a lossy line. The analytical calculation of the impedances on a lossy line, they are as general as we discussed earlier. So, those impedance transformation relationship using the hyperbolic cosines and sines, they are applicable for the calculation of the impedances on transmission line. So, with this minor modification to the analysis, the Smith chart can be used for moderately lossy transmission lines. And as we saw, if the line is very lossy, then it loses the meaning of transmission because it does not have a wave phenomena. So, that line then represents only some kind of a resistive network on which the power dies down as we move on the transmission line. Now, let us move to the important aspect of the analysis of transmission line, and that is the measurement of characteristic impedance of transmission line. Up till now we have said that a transmission line is there, it has a characteristic impedance which is given to you a priori, and then we proceeded and did the calculations on transmission lines. One can ask, if somebody has given you a transmission line, how would you first find out what is the characteristic impedance and what is the propagation constant on transmission line? So, as I had mentioned earlier, transmission line is characterized by the primary constants R, L, G and C, but normally for calculations of transmission line, we generally do not estimate these primary parameters. The secondary parameters, the characteristic impedance and the complex propagation constant, are enough, and therefore, for any unknown line we would like to estimate this secondary constant Z0 and gamma. So, the characteristic impedance and the complex propagation constant. Let us say now that I have a technique for measuring the input impedance which would be same as what we have discussed earlier for measuring the unknown impedances. So, let us say I have a setup which can measure an unknown impedance at a given frequency. Let us say now I want to measure the characteristic impedance of a line, which in general is a moderately lossy line or low loss line. This measurement now can be done by conducting what is called a short circuit and open circuit test of a section of a transmission line. So, first what we do, we take some length of transmission line. Let us say I have some length of transmission line which is L, the length is L. I take one end of this transmission line and connect to this setup which measures the impedance. So, this is the impedance measurement setup. So, if I connect the end of this transmission line to this impedance measurement setup, it can measure the input impedance of this line. Now, what do? We conduct the two tests. I measure the input impedance of this length of line by making the other end of the line short circuit and open circuit. So, I measure two impedances, input impedances, one with the open circuit condition at the other end of the line and one with the short circuit condition at the other end of the line. So, I get two impedances, let us say let them denote by ZOC and ZSC. So, ZOC is the input impedance measure at the input end of the transmission line when the other end was open circuited. So, as we know, this will be equal to the characteristic impedance cot hyperbolic of gamma L. Similarly, the input impedance when the other end of the line is short circuited will be given as Z0 into tan hyperbolic of gamma L. So, I know the physical length of the line, I can measure these impedances under the short circuit and open circuit conditions. Now, it will be immediately clear to you that if I take product of these two equations, these two will cancel and I will get a quantity which is Z0 square. So, once I conduct the short circuit and open circuit test, the calculation of characteristic impedance is straightforward. So, let us say I multiply these two and I get now the characteristic impedance of the line Z0, that will be equal to square root of ZOC and ZSC. So, the characteristic impedance is geometric mean of the input impedance of open circuited and input impedance of short circuited line. From the same two equations, if I take a ratio of these two, the Z0 will cancel and I may estimate the value of the propagation constant gamma. So, let us say if I take a ratio of this upon cot H gamma L, that will be equal to ZSC divided by ZOC. And cot H gamma L is 1 upon tan H gamma L. So, this quantity is tan H square gamma L, that will be ZSC divided by ZOC. Or tan H gamma L is equal to square root of ZSC by ZOC. Now, to get the value of gamma, I can first expand the hyperbolic tan and write them in the exponential form, and then can solve for the value of gamma L. So, if I write down explicitly, that will be, so the tan hyperbolic gamma L, that is equal to e to the power gamma L minus e to the power minus gamma L divided by e to the power gamma L plus e to the power minus gamma L. That is the quantity which is square root of ZSC upon ZOC. Just for the clarity, let me just call this quantity as some complex quantity A. So, the tan hyperbolic gamma L, which is equal to this, is quantity A. And since in general ZSC and ZOC are complex, A is a complex quantity. I can invert this relation, I can take e to the power minus gamma L common. So, this term will become e to the power 2 gamma L, and I can invert this. From there I can get e to the power 2 gamma L, that will be equal to 1 plus A upon 1 minus A. Let us write this quantity explicitly as the magnitude and phase term. So, let us say it has a magnitude r and it has a phase theta. So, e to the power 2 gamma L, which is e to the power 2 into alpha plus j beta L, that is equal to r e to the power j theta. So, separating out now the phase and amplitude term from here, essentially I get alpha is equal to 1 upon 2 L ln of r, that is equal to 1 upon 2 L ln of 1 plus A on 1 minus A. So, from this relation, if I take the real part of that, which is e to the power 2 alpha into L, L is the length of the line, which is now in capital L. So, this quantity e to the power 2 alpha into capital L, that will be equal to r. So, now substituting for this r in this, I get the quantity alpha, which is given by that. This has to be quantity which is magnitude, because r is the magnitude of 1 plus A upon 1 minus A. So, the attenuation constant can be calculated once you know this value A, which is related to the open circuit and the short circuit impedances. So, we get the ZSC and ZOC, square root of the ratio of these two will give me this complex quantity A. From this A, I can get this value R, and from here then substituting into this, I get the attenuation constant of the transmission line. Equating the imaginary part or the phase part of this term, we get the propagation constant beta, that is equal to 1 upon 2 L theta, that is the phase of this term. However, now when I am equating the phase of these two terms, there is the ambiguity of 2 pi's, multiples of 2 pi's, because the value which you will get for phase here is always modulo 2 pi. That means, when I calculate the value of beta, this could be e to the power j theta plus minus 2 m pi. So, I do not have a unique answer for beta because of this ambiguity of multiples of 2 pi. So, in general I will get the value of beta, which is theta plus minus 2 m pi, where m is an integer quantity. So, if I substitute the value of theta, that is from here, which is the angle of 1 plus a upon 1 minus a, then I can calculate the value of beta, but I will have an uncertainty that what is the value of m, how many modulo 2 pi's or how many multiples of 2 pi's have to be removed from here or added to get the right value of beta. So, from the short circuit and open circuit test, the calculation of attenuation constant is straightforward, but when I go to the calculation of the phase constant, there is an ambiguity because of the phase which is always modulo 2 pi. One may say that if I take a length of the line L which is less than lambda by 2, then I know for sure that this m is equal to 0. So, I do not have multiples of 2 pi. Then I have a unique value of beta, and that is the correct value of beta. However, if I take a length of the line which is less than lambda by 2, especially at high frequencies, this length of the line is very small. And since attenuation is very small on transmission line, the alpha generally is very small. So, for a small length of transmission line, the loss is not very significant. As a result, when you try to calculate the value of alpha, you do not get a very accurate number for alpha, because over the small length of transmission line which is less than lambda by 2, the line behaves more or less like lossless line. So, the estimation of the attenuation constant become unreliable if I take a small length of line which is less than lambda by 2. On the other hand, to improve the reliability of alpha, if I take a long length of the cable, then certainly I have now many more periods of the wavelength on this length of the cable or transmission line. So, alpha becomes reliable, but then I have to resolve this modulo 2 pi problem in the measurement of the phase. So, given this setup that we are measuring only the short circuit and open circuit impedance, we cannot resolve the ambiguity in the phase measurement, or we cannot measure the phase constant of transmission line reliably. So, what people normally do in practice, they do the measurement of transmission line at two frequencies. First, they do the measurement of the ZOC and ZSC, and from there they get the value of beta, which is ambiguous with 2m pi. Then we change the frequency slowly, so that I get now again the same value of the phase variation, and as a result now the number of cycles which we had on the transmission line are just changed by 1. So, by changing slowly the frequency on transmission line, if I make sure that now only one cycle change has taken place, the m is changed from m to m plus 1, I get the value of beta, and then from here now I can subtract in the 2, I can find out what would be the correct value of the propagation constant beta. So, by carrying out the multiple frequency observation or two frequency observations of ZOC and ZSC, I can find out the phase constant accurately. So, in practice, whenever we do the measurement of the characteristic impedance, that time we have to do the measurement at two frequencies, and then from there we can get correct value of the estimate of beta. Let us now consider two frequencies, f1 and f2, on which we carry the measurement of ZOC and ZSC. Let us say at frequency f1, I get some value of ZOC and ZSC, and from there I get a phase constant beta, and let us call that quantity as beta 1, that is equal to 1 upon 2L into theta minus 2 plus minus 2 m pi. Let us take the plus sign here. So, this is 1 upon 2L theta plus 2 m pi. Now, what we do is we slowly change the frequency and we go to a frequency where the ZOC and ZSC value again become same. Assuming that the length of the line is very large, by changing the frequency by a small amount, the attenuation constant alpha does not change significantly. So, what we are now essentially saying is, if I increase the frequency by a small amount, the number of wavelengths which are set up on the length of the transmission line, they are changed, and if they change by one cycle or 1 lambda by 2, then the loss does not change significantly, and that is the reason I get the same value of ZOC and ZSC. So, at another frequency f2, I will get a propagation constant beta 2, the value of alpha will come same, because by changing this frequency by a small amount, the attenuation constant is not changed. But since we have accommodated now one cycle of the wave on the transmission line, this quantity has become m plus 1. So, the phase constant beta 2 will be theta plus 2 into m plus 1 into pi. From here now, I can take the difference of these two quantities, and from here this term will cancel out, and what I will get is beta 2 minus beta 1, that will be equal to pi upon L. Now, we know beta 2 and beta 1, they are related to the velocity or the wavelength on the transmission line. So, this we can write as 2 pi into f2 divided by velocity minus 2 pi f1 upon the velocity, that is equal to pi upon L. From here then we can get the value of the velocity, that is equal to 2L into f2 minus f1, and the phase constant now beta will be equal to pi into f divided by L to f2 minus f1. So, what we have done, we did the measurement at two frequencies which are closely spaced in such a way that by changing the frequency from f1 to f2, the number of cycles of section of the line are increased by 1. Then from there we calculate the value of the velocity on the structure, and once we get the velocity, then we can find out the value of propagation constant, because from velocity we can find out the wavelength, and the 2 pi by wavelength gives me the phase constant on the transmission line. One would wonder at this point that why are we doing the estimation of the velocity on the transmission line? Doesn't the wave travel with the velocity of light on the transmission line? Or if we know the value of beta, can't we find out what is lambda, and from there we can find out what is the velocity? In fact, the problem is exactly opposite. The problem is, depending upon the structure, the velocity of the wave changes. Frequency is the one which is very sacred, but depending upon the propagation characteristic, the velocity changes or the wavelength changes, and therefore the phase constant changes. So, it is not that we know the wavelength from the velocity and we are trying to find out beta. In fact, beta is the quantity which is the most unknown quantity. So, for a given structure, we first estimate the value of beta, then 2 pi divided by beta gives me a number that we call as the wavelength, and that wavelength multiplied by frequency, that gives me what is called the velocity of the wave on the structure. So, in practice, the measurement of the attenuation constant and the phase constant. Have to go through these steps, but this is the method which we mentioned is the short circuit or open circuit measurement test. This is the most widely used test in practice for measuring the characteristic impedance and propagation constant on the line. Of course, there are certain practical difficulties that whenever we try to put the open circuit or short circuit at high frequencies, it is difficult to put a very good open or short circuit to the end of the transmission line. Even if we short the two conductors of a transmission line, there will be always some inductance at the end. If you leave the two conductors open at the end of the transmission line, there will be some fringing capacitance at the end of the transmission line. So, at very high frequency, realizing an open circuit and short circuit is not that straightforward. So, people make extra effort to develop this module, what are called the short circuit modules and the open circuit modules, which can be connected to the end of the line to realize a good open or short circuit. As I mentioned again, that getting an ideal open circuit or a short circuit is not very easy as we go to high frequencies. So, let me summarize what we have done today. We discussed very briefly the characteristics of the lossy transmission line. We also saw how do we make use of a Smith chart when the line is moderately lossy, and we also saw a practical method for estimating the characteristic impedance and the complex propagation constant of a transmission line.